Welcome back, College Algebra students. We are now in Chapter 6, Section 8. This is the last section of our current chapter. Most of our chapter is dealt with exponential functions and logarithmic functions. We're going to end our chapter with exponential growth and decay models, Newton's law, logistic growth and decay models. We're going to be taking a look at a variety of items in this particular section. A number of word problems. We're going to see the applications of what we have. So as we've taken a look at the exponential functions, the exponential function overall we could summarize as a b to the x. It's the exponential function because a and b would both be numbers. X is our variable and our exponent, or x is in the exponential position, or the exponent's position. Our variable is the exponent, as opposed to maybe something like a linear function where we have y equals mx plus b, where our variable is in the base position. Okay, so we do have some differences here. So we're focusing on the exponential function. So a was our initial value, b is our base, and sometimes we think about that as our rate of change. As we take a look at applications, one of the applications, financial applications in our last section, in this section we're going to have a sub t equals a sub 0 multiplied by e to the kt. So what we're saying here then is that the amount a of t varies over time. So the amount that we have is going to vary over time. So time is going to be our dependent variable here. So what is a sub 0? A sub 0 then is our original amount. We might have called that the initial amount or the initial value earlier on. So these values are the same. So the positions maybe change letters, okay, but the position still is going to end up being that initial value. So let's take a look at k. So if we have k is up here in the exponent position. K is going to represent then the rate of either growth or decay. So here's a question. If k is greater than 0, we're going to ask the same thing if k is less than 0. Would we have uninhibited growth or decay? Let's see, if k is bigger than 0, that means then that we would have a sub 0 e, and then k is going to be some positive number multiplied by t. So I'm just going to plus there as far as some positive. So we're going to take e as a base, as our natural growth rate, and multiply by itself a positive number of times. So if I do that, I'm going to keep getting bigger and bigger and bigger, so I'm going to be growing. When we take a look at k being a negative, that would mean that we have a sub 0, so our initial value, multiplied by a negative value of t. So since the negative is in the exponent, what that would lead us to then is we could do a sub 0, then divided by e to the positive t, because the negative in the exponent tells us to take the reciprocal of our base. So this whole thing here now becomes something we're dividing by. And if we end up dividing these values, okay, we're going to end up generally with what we call the decay. So that's the general concept of what we're doing. Graphically, we have this setup. So if our amount over time is some initial value multiplied by e to the kt, if k is positive, we're going to exponential growth, so we're going to be growing up this direction. And if k is negative, then we're going to be decreasing. So not a huge surprise rather, hopefully as far as we've gone through these. As we move on, so this is the general form, a of t, okay? I guess maybe the original general form was a equal, or y equals ab to the x. We changed the a of t. Previously, we had our financial items where it was a equals, let me just put this back up here, a equaled the principal times 1 plus the rate over n to the nt. So that was a formula that we had. So a variety of formulas. Take a look at this. One more variation on this as we get into another question, uninhibited growth of cells. So this model gives a number n of cells in a culture after a time t has passed. So in the early stages of growth, we could go ahead and follow this particular pattern where k is positive. Again, this is pretty much identical to what we just saw, where we had a of t equaled a sub 0 e to the kt. So all we're doing is we're shifting and adjusting some of these letters to kind of make sense for our context. So previously a was the amount. Now we're saying n instead of a, n for number. So Once we have this down for one scenario, all the other scenarios follow the same suit. So taking a look at our example here, example number one, and we've got, let's see, if I take a look ahead in my notes, we're going to be doing 1, 2, 3, 4, 5 examples, 6 examples today as far as our lecture. So 6 different applications, maybe not all applications, 6 different applications, but 6 different scenarios where we're using this exponential model. So let's take a look. Bacterial growth. So a colony of bacteria that grows according to the law of uninhibited growth is modeled by a particular function. Let's say our function is this function here. So n of t is 100 multiplied by e to the exponent of 0.045 t, where n is measured in grams, t is measured in days. So letter A, let's answer questions A through E. Let's determine the initial amount of bacteria. So on A, what we want then is n sub 0. So there's 2 ways we can find this. One is we take a look at position. So from our material up in the yellow box up above, n sub 0 is the initial number of cells. That's our first number out in front of our E. So in our case, we know that to be 100. Now, if we didn't remember that was the initial value, the other way we could have done that, so I'll put an or here, we could say, what is the number of cells at times 0? So at times 0, we would have 100 e to the 0.045 multiplied by 0. That would give us 100 e to 0.045 times 0 is 0, and 100 times e to the 0 with e to the 0 is 1, so we end up with 100. So our value, the initial value at n sub 0, or the number of cells at time 0, so our starting point is 100. So either way that we want to do those still works. Both end up doing the same thing. On letter B, we end up with a very similar item. What's the growth rate? So the growth rate, if we take a look back at our yellow box here, K is a positive constant that represents the growth rate of the cells. So this number in front of the T, so this number T here in front of that, that's going to be our constant growth rate. So this is going to be 0.045, and so that would be the same as 4.5%. Let me clean up my 5 here. There we go. 4.5% is our growth rate. So these first couple of questions, A and B, are basically reading position values in our formula. Let's take a look at the letter C. What is the population after 5 days? So what we're asking for in letter C is what is n when t equals 5. Okay? So let's take a look at our formula. So it's 100 e to the 0.045, and t now is 5. So that's going to equal, well, that's going to be something we're going to plug into the calculator. So let me go ahead and pull my calculator up here, clear out what I had previously. So move this off the side just a little bit. So we want to plug this into the calculator. So that's going to be 100 multiplied by e to a power. So second natural log gives us e to the x. And when we multiply, 0.045 times 5. And we end up with 125.2. And let's see, where we asked for a particular value, what's the population after 5 days? So we weren't asked a particular number of decimal places, so we'll just round this off to one place, so 125.2. That is the number of cells that we have after 5 days. Let's take a look at letter D. How long will it take the population to reach 140 grams? Okay, so now what we're asking, changing this up a little bit on part D here, put this off to the side, is I don't know what the time is to reach 140 days, but I want my number of cells to be 140. So if n of t originally was 100 e to the 0.045 t, and I want n of t now to be 140, then I have 140 equals 100 e to the 0.045 t. Now I need to solve for t. Okay, so we can go ahead and do that. So if I solve for t, I've got to get the term with t isolated by itself. So let me go ahead and divide both sides here by 100. So I can do that in my head. That's going to be 1.4, so just move the decimal over 2 places, equals e to the 0.045t. So I've got the t term by itself on one side, but it's in an exponent position. So if I could go ahead, we go back to the basic form of exponential functions. If I could get the bases here, so 1.4 and the e to be the same, then I could go ahead and ignore the bases, just work with the exponents. Well, I don't have a way I can do that. So what we're going to end up needing to do is we're going to end up using our logarithms. So what if I take the natural log of both sides, the natural log of 1.4, and that's going to be then the natural log of e to the 0.045t. Now, why did I choose the natural log? Now, on the left side, we still have natural log of 1.4. On the right side, natural log is log base e. So if I take log base e and then e to the 0.045t, what this means here is what exponent do I apply to e to get e to the 0.045t? So it's just 0.045t, effectively canceling out the natural log and the e. So we get 0.045t overall. Now it's a fairly simple process to finish solving this. I'm going to divide by 0.045, where they cancel out on the right side. So I've got t on the right, and then the rest of this is going to end up being something I again plug into the calculator. So we're going to end up with natural log of 1.4. Make sure we close off that parentheses. That's a very key piece. So we got to make sure that closes off. Then divided by 0.045. And we get 7.5. So 7.5 days. So 7.5 days into this growth, 7.5 days into this growth, we will have 140 grams. We'll have 140 grams of bacteria. Letter E, our last question. Listen, what is the doubling time for our population? Okay, so we want to know how long it takes for this to double. So what we're looking for here on letter E is we want n of t to be double what our initial value was. So twice n sub 0. So the one way to think about this one then is that we start out with n sub 0, we already said was 100. So we want to know, when does n of t equal then 200, because we know that n sub 0 was 100. If we take a look at our formula here was n of t equaled 100 e 0.045t. So we want to know, when do we end up getting 200? So we can say 200 here equals now 100 e to the 0.045t. So as we saw for t, that'll tell us when we ended up being double. So double of this 100. When we start solving this, we could divide both sides by 100. So that cancels on the right side. On the left side, we have 2 equals e, so 0.045t. Now, before we go on, I want to discuss this just briefly here. Anytime we want a doubling or a tripling or a halving or a quartering, whatever the case might be, I would always do that value multiplied by the initial value and put that on the left. But then when I divide by that initial value on both sides, it will always cancel on the right. So we'll end up with just our e to some power. And on the left side here, we'd end up with either a fourth or 2 or 3 if we're tripling, 4 if we're quadrupling. So it always works out that way. So two things we can do here. One, we can either logically work ourselves through with this box and then come up in here and fill it in. Or if I know I want to double, I can go directly to the second box, because if I'm doubling, it will always end up canceling out my initial value, and instead of n of t, I know I want n of t to be 2, so I immediately put the 2 into place. So like I said, it doesn't matter which way we do it, both ways will get us the same result. So let me get rid of my box here, and let's go ahead and finish solving this. So if I want to solve this, again, I've got an e and I've got a power, so the natural log makes sense. So the natural log of both sides. So the natural log and e cancel. So the natural log of 2 is 0.045. Whoops, forgot my t in there. Of t, I think, wait a minute, natural log of 2 is not 0.045. something was wrong, so I just missed my variable. And then I would have to, let's see, I would end up dividing by 0.045. So they cancel on the right side, and then I figure out what my value for t is. So what is my doubling time? So let's see, we're going to do natural log now of 2, and we're going to end up dividing this by 0.045. So we get 15.4. So it'll take 15.4 days to go ahead and double the number of cells, or this is the number of cells that we have in my population. Okay, so that would be the doubling time. So a variety of questions that we've taken a look at based off, put this up here, based off that law of inhibited growth, or the uninhibited growth formula. Okay, so as we take a look at that one, let's move on. Let's do another example. Another bacterial growth example here. So a colony of bacteria increases according to the law of uninhibited growth. So let's see, we can say again, n of t equals n sub 0 times e to the kt. So letter A. If n is the number of cells and t is the time in hours, express n as a function of t, well, what I just did up here at the top, that is letter A. So because I knew it was bacterial growth, I just wrote down, well, hey, if bacterial growth is going to follow this formula, letter A asks us, well, what is the formula? So let's move on to letter B then. If the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. So we want to figure out the function that's going to do this. And we know that we double in 3 hours. So one way that we can do this is that I know n of t in 3 hours. So n of 3 is going to be double n sub 0. So again, like we did last question, one way to do this is to say, all right, well, I want 2 n sub 0 on my left side. Is going to be n sub 0 e times k. And because this is 3 hours, that's going to end up being 3 as far as my variable up there. When I divide both sides by n sub 0, those cancel, so I get 2 equals e, and instead of k3, I'm going to write 3k. So two things I could have done. I either could have started off with this at the top, or since I know it's going to double in 3 hours, I could go ahead and put the 2 down immediately, ignore the n sub 0, and plug in my time as 3. Either one of those works, we get the same result in the end. So what we're trying to do here is we're going to try to figure out what k is. Like we did previously, we're going to need to do the natural log. So the natural log on both sides. Natural log and e cancel. So 3k is going to be natural log of 2. So when we divide by 3, we'll end up figuring out what our rate of growth is. Again, that's something we're going to do in the calculator. So we end up with natural log of 2 divided by 3. So our rate of growth here is 0.231049. So let's call it 0.23105. So we're going to take this out 5 decimal places. We're going to take this out a little ways because we're going to get better numbers overall as we keep on going. Now, I don't want to write maybe this whole thing. I don't want all 8 digits, but I take the first 4 or 5, and that's going to get me pretty close to anything I'm working with. So my overall function then, which was my question here, is going to end up being n of t equals n sub 0 e to the 0.23105 t. So that is going to be my overall function modeling the growth in this particular scenario. Letter C, how long will it take the size of the colony to triple? Okay, so now if we want to triple, I could say the shortcuts. I went 3 e to the kt. Okay, because that would be the tripling. Now, one other thing that I know here, though, I do know my value for k, because we just found that. So that's going to be 3e to the point, And what had we figured out there? 0.23105 t. And now we can figure out time to triple. So again, going to take the natural log. And one of the things I said at the beginning, hopefully we're starting to get the idea. Once you do one or two of these questions, most of the other questions follow along very, very nicely right afterwards. Natural log and e cancel. So natural log of 3 is 0.23105 t. Solve for t, we got to divide them by the 0.23105. Again, this is going to be something that we do in the calculator. So see, now we've got, instead of natural log of 2, we've got natural log 3. And then we're going to divide by 0.23105. So about 4 3/4 is going to be your time. And this is hours. So about 4.75 hours is going to be the time it takes to triple. So now that we have answered letter C, let's move on to letter D. How long will it take the population to double a second time? Okay, so that is to increase 4 times. So two ways we could do this. We could go back to something like letter C here and plug in 4. We could plug in 4 and 0.23105. And so down here at the end, we'd end up with natural log of 4 divided by that. Or the other thing that we could take a look at is we could take a look back at letter B, and we said, well, it doubles in 3 hours. So if we want it to double a second time, we need another 3 hours. So it's going to double in 6 hours. Okay. So just by reading through letter B, we know that it should be 6 hours. If we take a look at the calculation, so I'm going to say just by reading part B, it's got to be 6 hours. Let's take a look at the calculation. We would do 4 equals e to the 0.23105 t. Well, I know towards the end I'm going to end up with natural log of 4 now divided by 0.23105, and that's going to be t. So I'm going to end up skipping this whole section and just go straight to the end. And let's see what we end up with. How close are we? So I'm going to go back up here. I'm going to just up arrow twice. That way it copies that immediately. I'm going to go over here and just type 4 in its place. And we end up with 5.99997. That's pretty daggone close to 6. So why is it not exactly 6? The reason it's not exactly 6 is up here, we ended up with 0.23105 and we had rounded. So what if we take natural log 4, let's do it this way, let's take natural log 4, just an experiment here, and divide by this number. Now we end up with 6 because that's a more precise calculation. So as we go ahead and so we agree, as we go through these, the more decimal places we take out our rate of growth, like we did down here, the more decimal places we take that out to, the more precise our other calculations will end up. But typically, if we take these out to about 4 or 5 places, all the other calculations, when we start rounding to 1 or 2 places, are going to be accurate enough that we're going to be okay with the questions that we're working on. Let's move on to radioactive decay. So perhaps from high school science classes, we talked about radioactive decay and those sorts of things. So again, the same formula, A of t or n of t equals a sub 0 or maybe n sub 0 e to the kt. Because this is decay, k is going to end up being negative. So what changes on this? K is negative. Other than that, the ideas are still all the same. So let's take a look at an example here. So trees of burned wood, along with ancient stone tools in an archaeological dig in Chile, were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? So let's go ahead and take a look at, just write our formula down. So we know it's going to be something of this sort. A of t is a sub 0 e to the kt. Let me move this, give it some more space here. So what else do we know? We know from this last statement the half-life is 5,730 years. So half of the initial material is there after 5,730 years. So A of 5,730 is half of A sub 0, half of our initial value. So when our time is 5730, our value goes to half of our initial amount. So we can go ahead and do a substitution here. So A of 5730 is 1/2 A sub 0, but that's equal to this formula when T is 5730. As I've said before, what's going to happen is these A sub zeros are going to cancel out. So since we went to halving time, we'll take half of E raised to this power. So I'm going to rewrite it 5730K, because normally we write, a normal convention is write our variables second. Again, this looks very similar to things that we had just finished. And as we go to solve this, we're going to have to do natural log. So we got natural log of 1/2 equals natural log of E to the 5730K. Natural log of E cancels just like it had done previously. So now we got natural log of 1/2 equals 5,730K. So if we're trying to find K, our rate of growth, because we got to do that first here. So we divide by, I'm sorry, I divided by K. I don't want to divide by K. Divide by 5730. That way I end up with K by itself. So again, off to the side, bring up my calculator again. Notice the same types of things. It's going to be natural log of something divided by a value. So overall, same typical process. So in this case, natural log of 1/2. Now I could have typed in 0.5 also. That would have been fine. Divided by 5730. Now one thing to be certain, make sure we close off this natural log before we hit the division button. So now we end up with this value here. Let's talk about this just for a moment. What the calculator is showing is it's showing this decimal in scientific notation. So when the calculator says at the end E and then some number, that means multiply by 10 to the number that follows afterwards. So this is times 10 to the -4th power. In scientific notation, that means that we're going to move our decimal over. So this is -1.20968 E -4. Let me go ahead and move this back over so a little more space to write. This -4 really means multiply -1.20968 times 10 to the -4th. That's going to be our K value. When we multiply by powers of 10 with a negative, we make our value smaller. Because if we just think about it this way, as an aside, 10 to the -4 is the reciprocal of 10 to the 4th. That means 1 over 10 4 times. So that means 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10. So we want 1/10 times 1/10 times 1/10 times 1/10. So we want a tenth, so we're getting smaller and smaller and smaller. When we divide by 10 to make it smaller, we can just move our decimal over to the left. So if I move this decimal over, it's going to move over 1, 2, 3, 4, 1, 2, 3 extra zeros. So I'm going to end up with 0.000. It's going to be negative 0.00120,968, and that's my rate of growth. So why do I need my rate of growth? Well, I need that so I can go ahead and fill in this basic formula up here. So our basic formula then is A of T is going to be what our initial amount is, multiplied by E to the negative 0.000,120,968 T. Now we have our formula. So all of that just to get our formula. We still have not answered the a question. If the half-life is 5,730 years, approximately when was the tree cut and burned? Well, the other piece that we were told up in here is that we have 1.67% of the original amount of carbon-14. Okay? So that means after a certain amount of time, has passed, we have 0.0167 of our initial value. So that means then that I could rewrite this as 0.0167 A sub 0 equals A sub 0 E to the negative 0.000,120,968 T. Again, Basic principle, those a sub zeros are going to cancel. So I could have gone directly to 0.0167 equals e to the negative 0.0001209688t. So one of the things that we'll see when we do our half-life and our rate of decay is we do end up with some longer decimals here. Like I've said before, the basic principle is going to match up the same way. I've got an e here. To get rid of that e, I'm going to do natural log. So natural log of both sides. So the natural log and the e cancel. So I have natural log of 0.0167 equals negative 0.000120968t. To get rid of this value and get t by itself, I've got to divide by that. Going to divide on both sides. So those cancel. And so whatever I end up with here is going to be my t. And again, that's going to be something in the calculator. Same format. We got natural log, in this case 0.0167, because that's 1.67%, divided by my growth rates. That was negative 0.00012968. So approximately 31,557 years ago. Now, when we're doing the years here, it really doesn't make a whole lot of sense to take this out to a decimal equivalent, or what do I want to say here? Round this off to the closest tenth or something. That would be okay here. And so one of the things that I notice as I go ahead and type this in here is that I had a minor typographical error. So let me go back over here. When I was writing this down, let's see, when I was over writing this piece and over here, I forgot this 0 as a placeholder. Okay, so I need to change this. This should be 120968. So I just took a look at my notes and say, wait a minute, I got a different value. How did I get a different value to that? So I normally work these out before I go ahead and lecture on these. So let me go ahead and come back up in through here. And let me do an insert. Let me insert 0 here. And that's better. So we take a look at that one. 33,800. Let's call that 30 then. 33,830. Okay, so minor error on that, and that's one of the things I did not intend to illustrate it this way, but I was going to call attention to it, was just be careful. The more we write these things down, the more likely we are to go ahead and make a minor notation error. That's why I would encourage you to go ahead and write these down on paper as you're doing these for homework or for the quizzes or for the tests, and write down all your work. That way, if you're doing it on the homework and you get that immediate feedback as far as, hey, this question's or your answer is incorrect, go back through, make sure you didn't transpose a number or leave off a number, because typically those are the most common mistakes that we make. Okay, and that's one of the things that happened here as well. All right, so on this one, we did answer the question, how long would it take? So approximately 33,000 years on this one. 33,830 is our value. That's our final answer for this whole question. So in this question, we see, although it's not a very long in its writing, we did have a decent amount of work that we had to do in order to be able to answer the question. Okay, and so don't be afraid to use some space on your paper as you're writing things through. Okay. Now, one other item as far as a follow-up to the half-life. What if we say the half-life on something is 10 years? How can we figure out how long it will take before we get 25% of our material? Okay, so that might be a question that we ask. Okay, so let's see. If we start off, okay, we've got our whole amount here. That's going to be at time equals to 0. Once I do the half-life, so if I've got half of a sub 0, that's going to end up being 10 years. So if I want to go ahead and take another 10 years, that would take another half. So another half of that would end up being a fourth. So maybe I do it this way. Let me write it 100%. Half of that gives me 50%. Half of the half gives me 25%. So that would be another 10 years. That would give me 20 years. If I took another 10 years, so in 30 years, I've got another half, so that would be 12.5%. If I do another 10 years, so in 40 years' time, I got half of that, so that's 6.25% of a sub 0. So if we know the half-life and we want to kind of estimate approximately how long that would be. So if I want to know how long will it take to get about 20% of my data or 20% of my value, well, 20% is in here, so that's got to be somewhere between 20 and 30. So if we do a calculation and we end up calculating for 20% and we end up with 45 years, we know that we did something a little bit incorrectly. So this is one way we can think about the context of what we're working with overall. All right, so that was just an aside. So another application. Let's do Newton's law of cooling. So Newton said that the temperature U of a heated object at a particular given time t can be modeled by this particular function as we've got here in equation 4, where T is the constant temperature of the surrounding medium. So the surrounding medium typically is going to be either water, or it's going to be some liquid solution of some sort, or it's going to be air. U sub 0 then is the initial temperature of the heated object, and K is the negative constant. So if we're cooling off, we're going to end up here. So let's see what we have. So on our question here, an object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees. So if we start off with, let me pull this back down, didn't mean to move it all the way up there. If we go ahead and start writing this out here, what we have is, let's fill this in. So U of T, T, what is T? T is the constant temperature of the surrounding medium. So our air temperature here is 30 degrees. So that's our big T. Plus, then at U sub 0, what does it say U sub 0 is? That's the initial temperature of the heated object. So how much do we heat this object up to? Well, we heated the object up, it's heated up to 100 degrees. So that's the initial temperature. Minus capital T, so minus 30, is E to the KT. So what this is telling for us here is that our surrounding medium is 30 degrees, and we've got a differential here of 70 degrees. So if I actually do this calculation, that's going to be 70 times E to the KT. So eventually, this temperature here is going to get down to 0 as far as that rate of change or that growth. So eventually we'll end up being the temperature of our surrounding material. Eventually we'll get down to that. Okay. Shoot, we just answered letter C. Okay. So what letter C is asking is, what do you notice about the temperature as time passes? We're going to eventually end up with the temperature of our surrounding medium. So eventually we'll get close to 70 degrees. Okay. Now, we have not answered part A yet, so let's go ahead and get to part A. We've answered part C already, but let's go back to part A. So if the temperature of the object is 80 degrees after 5 minutes, when will its temperature be 50 degrees? Okay. So what do we know here? We know then the temperature is 80 degrees after 5 minutes. So U of 5 is going to end up being 80. So 80 degrees. So let's see, if I go ahead and plug this into our formula here now, let's see, so U of 5 is 80, so 80 equals this idea when T is replaced by 5. So I'm going to replace this T up here by 5. So it's going to be 30 plus 70 E to the 5T, okay? So we'll go ahead and fill that one up. Whoops, wait a minute. My T is 5. I want 5K. So I'm trying to figure out what K is in this case. So let's go ahead and solve for K. Figure out what is. Once we figure out K, then we can go ahead and figure out what the temperature will be, or how long it takes to get the temperature down to 50. So we have to figure out our K value first so we can fill in the rest of this formula. Okay, so let's see, we're going to subtract 30, so that would be 50 equals 70e to the 5K. So let's divide both sides by 70. Let's move logistic models down here a bit. So let's see, those 70s cancel, so that's going to be 5/7 equals e to the 5K. Surprise, surprise, we're going to apply the natural log to both sides. Natural logs cancel, so we have natural log of 5/7 equals 5K. So divide both sides by 5, and we'll figure out our value for K. Let me clean this K up here. Pull up my calculator again. So we're going to do natural log of 5 divided by 7. Close that off, and then let's divide that whole value by 5. So as expected, we get a negative value because we're decreasing. So at negative 0.067, let's take it 4 places out here, 1, 2, 3, 4, 0.0673. Okay. So now let's see. We know that this equation here we can rewrite. We can now rewrite this equation as saying our temperature after T amount of time will be 30 plus 70 e to the negative point, what did we just say here? 0.0673 times T. So that's now our formula that we're going to use. Now we can answer the rest of letter A, because letter A is asking us, okay, when will its temperature be 50 degrees? Okay, so when will the temperature be 50? So when will U of T equal 50? That's our idea. So we got 50 now equals 30 plus 70 e to the negative 0.0673 T. So let's go ahead and we'll subtract 30 from both sides. So we end up with 20 is now 70 e to the negative 0.0673 T. We divide both sides by 70. 70's cancel, so 20 over 70 reduces to 2/7. E to negative 0.0673 T. Natural log both sides, those cancel. We'll end up dividing by the negative 0.0673. And that will tell us our T. Okay, so back in my, oh, I'm sorry, I just recognized I had the calculator up that whole time, and I was writing underneath it. My apologies for that. So overall, let me go back just to illustrate what I was doing. So I rewrote this formula in the box down to the U of T is 30 plus 70e to the negative 0.0673 T. Then our question is when, so U of T, what's our time when U of T is 50? So, and this is a question mark over here. So we have 50 in for U of T, and then U of T equals this whole thing. So we just wrote that down. Then we subtracted 30 from both sides to make this 20. Then we end up with 70 of this whole value on the right. If we divide 70 on both sides, 70 cancels. So 20 over 70 is just 2/7. Once I apply the natural log on both sides, the natural log and e cancel. Then we divide by negative 0.0673 on both sides, and then we're ready to find T. So my apologies for writing underneath the calculator here. So we'll end up with natural log of 2/7, and we'll divide by negative 0.0673, and we'll end up with, let's see, 18.6. Close my calculator out there so we can see what we have. So that was, let's see, 18.6 is how long it takes for our temperature to drop to 50 degrees. And time here is in minutes, so this is 18.6 minutes. That's how long that would take to drop down then to 50 degrees. Our next question, question B, asks us determine the elapsed time before the temperature of the object is 35 degrees. So very similar question as far as letter A. Okay? So letter A basically was from here on. So letter B, let's see, we want to change the 50. We just different change colors here. We want to change 50 to 35. Okay, so that's going to mean 35 equals 30 plus 70 e to the negative 0.0673t. So all of these numbers are going to end up being the same, except down here at the end, this 2/7 is going to be 35 over 70. So 35 over 70, okay, is a half. So natural log of a half is going to equal, see, e to the negative, actually, we can go ahead and get rid of that. Natural log is going to be, natural log and e is going to cancel out, negative 0.0673t. So we could divide both sides. Oh, you know what? I made a mistake. I'm trying to shortcut this. I would do 35 over 70. I forgot about this 30 up here. I got to take that out first. My apologies. Every once in a while, when I take a look at these, I think, oh, we can just shortcut this so I can do it in my head. Sometimes at work, other times we take a look and go, no, just slow down, take our time through here. So let's subtract the 30. So that gives me 5 equals 70e to negative 0.0673t. Now divide by my 70. So it's not 35 over 70, it's 5 over 70. All the other values remain the same. Then, like we've done previously, we can take natural logs. The natural log and e cancel. So natural log of 5/70ths. Now, I could reduce this if I want to. Since I know I'm going to plug in the calculator, I'm just going to leave it as 5/70ths for now. And negative 0.0673t. We will then divide both sides by this decimal. And I've learned my lesson to go ahead and make sure I slow down now. Make sure I don't lose any decimal positions either. So those disappear. I'm left with t. Let's see what we come up with on our calculator. So we have natural log. And one reason I would have caught this is that the numbers here would have been quite a bit different. So let's see, we've got 5 over 70 divided by, again, our negative 0.0673. So we end up with approximately 39.2 minutes. Minimize my calculator, so make sure I do that so we can see everything that we have. Okay? So what we've done then is we've calculated on this particular question with Newton's law of cooling. Okay? We first had to go ahead and come up with what is our formula. So we have to write our initial formula out in through here, fill in our parts and pieces. And once we filled in our parts and pieces, use the first information, okay? So it was 5 minutes, we were 80 degrees. Fill in the 5 minutes and 80 degrees to find K. So then once we find K, then we could plug that back in and get an overall equation that has K filled in. Then we have our equation with just one variable, because up in here in this black box, I have two variables. I have K and T. In order to solve something, I need only one variable. I can only have one variable. So I need to find K. Once we found K, we substitute that in there. So then we ended up knowing what our equation is, or our formula rather. And then the rest of A and B are fairly simple to go ahead and calculate. Okay, so to get down to 50 degrees from part A took us 18 minutes. To get to 35 degrees took us 39 minutes. So what we're seeing as time increases, our temperature is indeed certainly decreasing along the way. So that is Newton's law of cooling. So as we take a look at our next example, we've got logistic growth. So as we take a look at logistic growth, we see that the exponential model, A of t is a sub 0 e to the kt. As k is positive, that assumes uninhibited growth, meaning the value grows without limits. So this would pose a bit of a problem if we've got a bacteria that's growing, grows without end, that would be problematic. One of the things that we recognize as far as situations that occur in nature is that if we're talking about cell division by chance, and in this particular case we are, recall that cell division can be modeled using this function, assuming though that no cell dies and no byproducts are produced. But cell division eventually is limited by factors such as living space and food supply, such as lily pads in a pond. They can only grow so much before they've covered the entire pond, and they're out of space. The number of fish in a pond maybe can only grow to a certain number of fish before the oxygen is depleted, the food sources are depleted, and we can't do any more. So as we take a look at these limiting factors, we have what we call the logistic model. So the logistic model limits then this exponential growth overall. So let's take a look a little bit further detail at our logistic model. So we have equation number 7 here. And in this model, the population P after time T is given by this overall function. So this is what we're going to be taking a look at. So what are the parameters and the caveats on this function? Let's see, A, B, and C are all constants. A is positive and C must be positive. We're growth if B is positive and decay if B is negative. Okay, so if B is positive, we're growing. If B is negative, we're decaying. C then, overall, as far as position, C is called the carrying capacity. As we take a look at the graph, as we go towards infinity, notice then that we end up with a horizontal asymptote at C. So that's the highest value that we can get up to. So if we are growing, okay, if we are growing as a function, we're going to grow to a certain amount and then cap off. We could be decaying, means we start at our highest value, and then we go slowly down, or maybe not slowly down, but we decrease until we get to another horizontal asymptote. I didn't mention this, but there's another horizontal asymptote at 0. So this graph is bounded above by the carrying capacity and bounded below by 0. Another interesting piece here is whatever half of the carrying capacity is, so half of that, when that occurs, that's going to be what we call the inflection point. So what is the inflection point? So that's going to be when our graph starts changing how it's bending. So if we're growing here, we're concave up, we're bending in upward direction. After our inflection point, we start bending down. So our rate of growth is after this point, starts declining. So we're not growing as quickly, and eventually we're not growing hardly at all, and then we get down to just our carrying capacity. With our decaying function, or decaying our decaying model here, I should say, our decaying is very quick, and then eventually it slows down, okay, and then we level back off down to 0. So that would be our logistic decay. So that inflection point, okay, the inflection point overall is half of the carrying capacity. Okay, so we've talked through this function. If you take a look in the textbook, they will also give you this particular box. These are the properties, and we already took a look at effectively all those properties when I was describing the graph that we had been looking at. So let's do an example now of a carrying capacity question. So let's take a look and say the fruit fly population. And I'll say that one quick 3 times. Fruit flies are placed in a half-pint milk bottle with a banana for food and yeast plants for food to provide stimulus to lay the eggs. Suppose that the fruit fly population after T days is given by this model. So that model is indeed then the same way that we have in our logistic growth model. So it's our logistic model where C is the carrying capacity down there. Okay, so let's see what we end up with here. So letter A, let's state the carrying capacity and the growth rates. Okay, so let me get my pen instead of my highlighter. Okay, so the carrying capacity. So what is the max that we have here? So our carrying capacity is just our numerator. That's going to end up being 230. And our growth rates, our growth rate here is going to end up being the value with T. Now, our growth rate, we're going to go ahead and take its absolute value. So we're going to say this is 37%. We're not going to take a look at negatives or positive. We're just always going to list the positive value. Okay. For letter B, let's see, we want to know what's the initial population. So the initial population is at times 0. So at times 0, that would be 230 over 1 plus 56.5e to the negative 0.37 times 0. So if I plug 0 in for time, 0 needs to go in for time over here also. So what we will note then is we got 230 over 1 plus. Now, negative 0.37 times 0, that's all going to go to 0. E to the 0 is going to be 1. So we got 1 plus 56.5. So that's going to end up being 230 divided by 57.5. Guess what? We're going to use our calculator again. We'll move this over a bit to the side. So we'll clear this out. So we will have 230 divided by 57.5. We end up with 4. So our initial amount here, so our initial number is 4. So that's A and B. Let's see, what's the population after 5 days? Okay, so we just calculated P of 0 was our initial. Now we want to know, well, what's P of 5? Okay, so we can just plug that into our calculator to write our formula down first here. So let's see, P of 5 is going to end up being 230 over 1 plus 56e to the negative 0.37 times 5. Again, I'm just going to take this and plug that into the calculator. So I've got, let's do it this way. Get my template here. So I've got 230 over, let's see, 1 plus 56 times e to a power, and that power is negative 0.37 times 5. So the nice thing about our calculator is that can look just like what our paper says. And we end up saying, okay, so P of 5 is going to be approximately 23. Let's see, to tell us how many, to round this to, no, it did not. So let's say approximately 23.5. So that's letter C. Letter D, how long will it take the population to reach 180? Okay, so we want our population. At what time is it 180? Okay, so what we'll do is then we'll set 180 equal to this other function, so equals to 230, 1 plus 56. Was that 56.5? Did I miss? Oh, I did, didn't I? I apologize for that. This up here should have been 56.5. Let's see how much that changes our value. I apologize for that. Again, slight typographical error. So I'm just going to, what I'm going to do, instead of retyping the whole thing, copy and paste over here. And I'm going to do a second delete, which inserts. Let me put a decimal. Whoops. Let's do 56.5. Whoops. Let me insert. Multiplied by e to the negative 0.37. All right, so now we've got it. Okay, so then slightly lower, 23.3 in this case instead of 23.5. So it didn't change that value much, but it did change it. Now, if we were rounding the closest number, whole number, would not have changed our value at all. Closest tenth would have been an incorrect answer because I forgot that decimal point. So found that out because I was writing this one down here, e to the negative 0.37. In this case, I don't know what that time is, so that's got to remain t. So as we take a look at this, one of the things that we're going to have to do is we're going to need to isolate this t term. So we're going to need to isolate this whole thing here. Problem is, it's in the denominator of a fraction. So what I need to do is going to multiply both sides by that denominator. So if I do that, I'm going to end up with 180 multiplied by 1 plus 56.5. Let me be very cautious here and tedious. 56.5 e to negative 0.37 t equals, then on the right side it would have canceled, so it just would have been 230. Then I'm going to end up dividing by 180 to get rid of the values on the left. Now I have 1 plus 56.5 e, it's negative 0.37 t equals, and let's cut the zeros out, so let's call it 23 over 18. Now I still want to get this t by itself, so I got to get rid of this 1, so I'm going to subtract 56.5 e to negative 0.37 t equals 1 minus 23 eighteenths. So, excuse me, I'm subtracting the 1, so I want 23 eighteenths minus 1. Now that reduces quite nicely here, because 1 as far as eighteenths would be 18 eighteenths, so that's going to end up being 5 eighteenths. Okay, so we'll go ahead and call this 5 eighteenths. Then I'm going to divide both sides by 56.5. So e to the negative 0.37 t equals 5 eighteenths divided by 56.5. I was going to say 57 for some reason. Then we're going to have to apply natural log. So natural log and the e cancel. So we got negative 0.37 t equals the natural log of 5 eighteenths divided by 56.5. Then to finish solving this, we're going to end up dividing by negative 0.37. And that finally will get me my t value. So some fairly tedious work here to go ahead and get these in the right format. So let's see what we ended up with here. See if we got the right value, the same values I made previously. So we got a fraction here. So let's go ahead and do our fraction. So I've got the natural log. Let's see, natural log of, and let's see, I want 5 eighteenths. So I'm going to do 5 divided by 18 in parentheses, then divide that by 56.5. Oops, and so 56.5 at 56.5. Okay, then divide that by negative 0.37. And we end up with 14.4. So some tedious work in the calculator, some fairly tedious work here as far as solving the equation. However, as we take a look at these, no one single step is particularly difficult. It's just we have a lot of steps to do. And I've illustrated for us, unfortunately, in this video, to be mindful of not forgetting a decimal or transposing a number, because that does change our answers, obviously. So that was letter D. Let's take a look at letter E. Using a graphing utility to determine how long it takes, or use a graphing utility rather, to determine how long it takes for the population to reach 1/2 of the carrying capacity. So we want to figure out, when does this equal, let's see, our carrying capacity was 230. So half of that would be 115. So remember, our carrying capacity was this top number. It's what we figured out down here at the base here in letter A. So half of that is just 115. So that's the thing I'm looking at now. Let's go and take a look at this. So what we will do is we will plug in. So if we're using our graphing utility here, we'll plug one side into y1, we'll plug the other side into y2, and we'll see where they intersect each other. So let's go back to y equals. So we did this in a previous example where we set some values in here. So let's say this is, let's get my fraction template in here. So this is 230 over 1 plus 56.5 times, what do we have, e to the negative 0.37. Now I can't type t because in the graph calculator everything's in terms of x. So I'll go ahead and type in x here. And so I have that one. Then I want this to, second value to be 115. Now, when I graph this, if I go ahead and do zoom standard, as far as my standard graphing, I see the exponential come up through here as far as P of t. I don't see the 115 because this is counting by ones. So 115 is way up off the screen. So what I need to do is I can go back to my window and change the settings. So let's see, let's change our y values. Let's go maybe from 110 up to 120, and we'll see what we end up with. And yeah, counting by ones is okay. So let's go ahead and now graph this. So that is my value as far as the 115, but now I don't see the rest of my graph over here. So another thing we can do, that means that our exponential growth is probably way out over here somewhere. So we end up with these dilemmas at times. So let's go ahead and do zoom. There's another type of zoom we can do. Let's do 0, which is zoom fit. That way we end up seeing where both of these are. So I do see both of them, but I want to see where this is over here a little bit. So what I'm going to do is I'm going to go ahead and zoom out on number 3. Notice I can go ahead where this cursor is. I can zoom out wherever that is. So I'm going to move this up a little bit so I can see back over into this area. Okay, so let's go from there. Now I see this much more clearly. Okay, so what I want to do is I want to see where these intersect each other. So let me go to the second trace commands. That's going to be the intersection, which is number 5. First curve is okay. Second curve, all right. Guess, yeah, that's a pretty good guess. So we see at their intersection, when are they the same? At about 10.9. Okay, so when I go ahead and come back over here, how long will that take? When t is approximately, I forgot what that number was, when t is about 10.9. Okay. Now, the other way we could have done that is instead of doing this in the calculator, could we have went ahead and solved this? I mean, that's what we did. That's what we did over here on letter D. Okay, we just went ahead and typed 180 in here and solved this, and we ended up with 14.4. If I could have done the same thing, but instead, just wanted to demonstrate that we can use the calculator, and as we use the calculator, we get some other values. Okay. All right, so that wraps us up for this particular video. There was one more example I was going to be taking a look at, but this video has already run over an hour. We're looking at an hour, 7 minutes so far, so I think we're okay without having that last example. It was another example of, let's see, of the logistic model. Okay, just would have been another example of more examples of doing that. So we'll go ahead and stop here. If you've noticed a mistake, please go ahead and email me and let me know. Otherwise, I'll see you in another video.